What we're going to look at on page 6 and a little bit of page 7 actually is we're going to look at this right here. It's called a heating curve. And this heating curve, what it shows is it shows time versus temperature, meaning as time progresses on the x-axis, the y-axis shows what happens to the temperature of something when it heats up. So the example we're going to use is we are going to start with solid ice and what happens to it when it actually turns into steam. So you guys can see that this first diagonal line right here, it goes from some negative number up to 0 degrees. So what's happening at that line is it says here that step A, which is going to be this blue line down here, step A is a rise in temperature as ice absorbs heat. So at this point, this is still a solid. Ice doesn't melt until it becomes 0 degrees. So as of now, when it's however cold it is, and as it gets up to 0 degrees, it's still going to be a block of ice. Now, when that block of ice actually turns, it actually gets to 0. What happens then in this line here, this flat line, I'm going to call that B. What is happening at that line is it says the ice melts to the liquid phase. So this is going to be that melting phase. And this is at point B. That's going to be where a phase change occurs. So again, we said that we can use that Q equals MC delta T, the Q equals M cap, and we can use that when a substance is warming, but phase changes are different. Now, I want you guys to notice that this yellow line here, line B, that's a flat line. So that means that when things go through a phase change, when a substance goes through a phase change, it doesn't change temperature. So you guys can see that it even says it in the chart, that the temperature does not change. It stays at 0 degrees. So when a block of ice is melting, that is going to go through and stay 0. Now, once that entire block of ice melts, this next part, which is this line here, that's going to be your line C. Line C is when it's a liquid. Now, you guys know obviously liquids can be a lot of different temperatures. Um, if you're drinking, if you warm up water to make hot tea, obviously that liquid would be very warm. If you are drinking something that's been refrigerated, that liquid would be very cold. So water stays a liquid from 0 to 100 degrees. Now, if you continue to heat up that water and it actually gets to be 100 degrees, at that point, you have another flat line. At that point, line D, this is where you have the water boiling. And that's going to be another phase change. So notice that those flat lines, those are your phase changes. As time goes on, the temperature doesn't go up or down. Now, once that entire sample actually boils and turns into a gas, then if it continues to get hotter, now you have this last line where the gas is warming. So once it's at 100 degrees, the gas can warm up until however hot it gets. So once it's above 100, then you're just at a gas. So if we notice here, it says the diagonal lines represent a substance warming without phase changes. So you have at the bottom here, you have this blue line, and this can be, as cold as ice is. So anything that is 0 degrees Celsius or below, that's going to be your solid. Then, like I said, this phase B, this is going to be a phase change. And that phase change is going to be melting. So what you have here is you have a block of ice that's cold, it hits 0 degrees, it melts. Then at that point, once the entire thing melts, then you have this liquid warming. So ice, anytime it's between 0 degrees Celsius to 100 degrees Celsius, then it's going to be a liquid. Now, once after that liquid, once all of that liquid gets up to 100 degrees, there's another phase change. That's when it starts to boil. It stays at 100 degrees while it boils. And then after that, that's when you have the last part is the gas. Anytime it is 100 degrees and higher, that is when you're going to have a gas. So you guys know this process. You understand this. You know that ice, as it heats up, eventually is going to melt. Liquid, as it eventually heats up, it's going to boil. And then gas can also get warmer. You guys understand this. It's just putting it into an actual scientific graph where you're looking at the heating curve. So these numbers, this 0 degrees and the 100 degrees, remember those are important because 0 degrees is the melting point of ice or water, and 100 degrees is the boiling point of ice or water. Now, what we're looking at down here is it says a phase change requires significantly more energy to occur than just warming up a substance. So when you're warming something up, all you're doing is you're speeding up the particles. So for example, if you have water and you put it on the stove and it's not boiling yet, it's just heating itself up. All you're doing right there is you're overcoming the forces. You're just speeding up those particles. What you're doing with that is you're just making, you're increasing the kinetic energy. We talked about how temperature is based on kinetic energy. So when you heat things up, kinetic energy increases, the particles move faster. Now, during the phase changes, and this is what this part is saying, is during the phase changes, you actually are think of a solid. Those particles are really close together. When a solid melts and becomes a liquid, you're actually overcoming those forces of attraction and you're moving those particles far apart from one another. So that's going to take significantly more energy. Now, during phase changes, we use something called delta H as opposed to C. So before, and I'm going to flip over to page 7. Before we talked about C, that specific heat capacity had to do with how much energy it takes to warm up a substance. Now with delta H is talking about how much energy you need for a phase change. So there's two different delta H's. There is heat of fusion. That's the amount of energy needed to convert a solid to a liquid. So essentially how much energy it takes to melt something. Then there's also called a heat of vaporization, which is the amount of energy you need to essentially boil something. So these heat of fusions and heat of vaporizations, again, this is just how much energy is required for a phase change. I'm going to go ahead and stop this video here, and then you guys can go ahead and watch the page 7 video, and that's when we're going to talk about the next part with collision theory.